So the next speaker is Théo Fabris, and he is going to talk about separations of monotone and non-monotone algebraic models.
Thank you. Hello everyone, my name is Théo, and I'm going to explain why negations are powerful even in small depth today. And this is a joint work with Bruno from Oxford, Parto from Chennai, and Shpilka and Yehudayoff from Copenhagen. I need to pass my slides. Good. Okay, so my plan for this talk is just to give you a few definitions, just to make sure that everything knows the definitions. Everyone knows the definitions, and then I'm gonna state the main results of this paper and then prove it. And then if I have time, we can talk more about further results, which relates algebraic complexity and Boolean complexity in the monotone setting. And then I'll finish with some conclusions and open questions. Okay, so in computational complexity, we categorize our problems into classes, and then we want to just understand how those classes are related to each other. And then we have a class C1, which pick your two favorite classes, and then you want to understand how they're related. In particular, you would like to be able to prove that there exists a point in C2 that is not in C1, which means that you want to prove that, or prove a lower bound for C1 that the level of explicitness of that lower bound is in C2. That is, there exists an upper bound in C2 that you can show that nothing in C1 can that it's not in C1. And for this work, C1 for us will be a monotone class, a fairly strong monotone class in the monotone size hierarchy, and C2 will be a fairly low depth class. So we want to compare the power of monotone circuits with the power of low depth circuits. Good. And okay, now I'm going to give you a few definitions. In the monotone world, the main objects are monotone polynomials, which are just polynomials where all the coefficients are non-negative. And the main examples are the clique or the permanent, which counts the number of perfect matchings in bipartite graphs, and it has this nice expression. And also the clique polynomial that counts the number of k-cliques in a graph. And okay, those are just examples to keep in mind. And the main model of computation that we're going to consider today are algebraic circuits that we have been seeing since the last day, so I'm going to go very quickly over it, which is an algebraic circuit is just a DAG where you put labels in your nodes, like it's a directed acyclic graph, you put labels in your nodes, and you compute polynomials in the natural way. You start at the leaves, you already know the polynomials there, and then you combine it, you get the output gate. And then the output of the circle will be, the polynomial computed by the circle will be just a polynomial computed at the output gate. And the measures that we care about are the size, which is the number of nodes, and the depth, which is the maximum distribute distance in this DAG. And we say that the circuit is monotone if no gate, if no label that we use in this DAG is a negative real number. Because here we are working only over the reals. The field is the real, so negative numbers are well defined. Okay, good. So our main result is this construction, which we show that there exists. We construct an n-variate monotone polynomial P such that we can compute P with a very small depth tree circuit, which is the first result. I guess you cannot see, but it's the number one over there. And the other property of P is that any monotone algebraic circuit computing P has size at least 2 to the n. And P is a degree n polynomial, so the second icon over there cannot be improved further, so this is like an optimal lower bound an optimal monotone algebraic lower bound. And the depth can also not be reduced further, because for depth 2 we cannot do, for depth 2 we can convert the depth 2 to a monotone depth 2 easily. And the size is already polynomial, so except for like finite grained improvements in the exponent, we cannot do much better. So that's why I claim that this is the best possible separation. And as a corollary of the, as a consequence of our choice of polynomial, we can also obtain a strong separation for constant degree polynomials. And I'm going to explain that later, but this solves an open question in the survey of Amir and Amir. And okay, but the main idea to prove this lower bound is to first reduce the second bullet point, to prove in a multi-partition communication complexity lower bound for a certain Boolean function. I'm going to explain later what that is, which was a connection that was already known before. And then the first item over there will come from the fact that we proved a strong lower bound for a very simple function, and I'll explain later why that function is simple. Okay. And so in pictures, what are our main results? Here we have the depth hierarchy in the algebraic setting. Here we have all the monotone polynomials that today we only care about monotone polynomials, so just like look inside this box. So here's the depth hierarchy with respect to the only monotone polynomials. It's not the monotone depth hierarchy, but just the depth hierarchy with respect to monotone polynomials. And now we want to compare this horizontal hierarchy with the circuit size, monotone circuit size hierarchy in the algebraic setting. And okay, the results of the kind that I just stated for you were proved first in the 80s by Valiant. He proved an exponential lower bound for a function for a polynomial in VP. He proved this thing. And this implies already a superpolynomial lower bound over there. Those are superpolynomial lower bounds. Those lower bounds, those results here are exponential lower bounds. And the ones that I'm going to show later here will be the strongly exponential lower bounds. And okay, so Valiant did this one in the 80s, and recently it was improved by Chattopadhyay, Datta, and Parto, one of our co-authors. They proved this. They improved the explicitness of Valiant's lower bound. Like they proved for a different polynomial, but they got VAC0 polynomial that cannot be computed by exponentially sized monotone circuits. And later this was improved. Valiant's lower bound was improved to a strongly exponential lower bound for another polynomial. And our results improved this result and also all the other results in the sense that we prove a strongly exponential lower bound for monotone circuits where the polynomial that we computed is a depth 3 circuit. So it's even the lowest level of the depth hierarchy inside VAC0. Good. And about the optimal separations that I mentioned before, we could ask this natural question. We have a general circuit computing a polynomial of constant degree. Can we convert that circuit into a monotone circuit with size better than the trivial bound that will be just to expand the polynomial and put all the monomials in construct depth 2 circuits of the same size? And this was the question asked at the survey. And this is a natural question because we know that for many other restrictions in the algebraic setting, if the degree is small, we can do non-trivial things. We can do things better than the trivial bound over there, like the trivial expansion that we have. But unfortunately for the monotone case, the answer is no. And the answer is no because we proved this corollary from our theorem. We construct a monotone polynomial P such that P has n variables and degree k, and we can compute P by a depth 3 circuit of small size, and any monotone algebraic circuit computing P has size at least n to the k. And the main idea is to reduce the degree of the polynomial that we used before, and then we show, okay, we have a sum encoding argument of for the monomials from the previous polynomial that we had. And then we need to argue that our lower bounds and upper bounds are robust with respect to this encoding. And this kind of this robustness of the lower bounds and upper bounds, the lower bound is most of the previous lower bounds were known to be are probably robust with respect to this monomial encoding in some sense. But the hard part is to show that we can reduce the degree of the polynomial and still get the same upper bound. And this was the part. This robustness of our upper bound comes from the fact that our upper bound is very simple, as I'm going to explain later. So, okay, those are our main results. So now it's a good time to ask questions if you have any, because otherwise I'm going to start to prove things. It's going to become harder and harder.
Is K assumed to be smaller than n in this corollary?
K is a constant.
Okay.
And n, you imagine that n is a group, it's a sufficiently large natural number.
Okay.
I forgot to say that. Okay, thank you. Anything else? Good. So let's prove the first theorem. So what is our goal? We want to construct a polynomial p that can be computed by a small depth-free circuit, and we want to show that any monotone algebraic circuit computed p has size 2 to the n. And the construction will be, we use some expanded graphs, as we're going to see later. And so let's just pick any expanded graph that you like. With n vertices, that's the important thing. And now we define a Boolean function with respect to that expanded graph. And here, throughout the talk, I'm going to use the correspondence between the hypercube, and Boolean hypercube, and subsets of vertices, so just be aware of that. And we say that this Boolean function maps sets to 1 if and only if the graph induced by the set has number of edges different from 1. And okay, so that's the definition of the function. And one nice property of this function that I said before, this is simple. This function is simple because of the following thing. We can say that we can characterize whether a point in the hypercube is 1 for this function, that is the function evaluated at that point is 1. If and only if polynomial q that the polynomial q above, defined above, is non-zero. And then, why is that simple? It's simple in this sense is just because this polynomial q is sparse. Like the sparsity of this polynomial is the number of edges squared, and the number of edges is roughly n. So the sparsity of this polynomial is n squared. And then, okay, now we define f, q. Now we're going to define the polynomial that we're going to get the results over there. And the definition is very simple. We sum over all the subsets of n, and for each subset of n, we put the coefficient q of the for the monomial for the multilinear monomial associated to that set, we put the coefficient q. We put as a coefficient q evaluated at the indicator vector of s, which is this thing over here. And then one nice thing about this polynomial p is that using that correspondence over there, we can see that the support of this polynomial has there's a bijection between the support of this polynomial and the ones of the function. And this is one thing to keep in mind. And okay, now I'm going to use a few lemmas that were proved before our work. The first one is from a paper of Shpilka and Yehudayoff. They show that for any polynomial of this kind, we can show that if Q is S sparse, then we can get a depth-free circuit for P that is computed that has size S times N. And in our case, S is N squared, so now we got the upper bound over there. So now we're happy, we already have the upper bound, now we just need to prove the lower bound. And the idea to prove the lower bound is to use another lemma by Raz and Yehudayoff, where they show that if P is computed by a size S monotone circuit, we can pick that circuit and obtain a multi-partition rectangle cover for F of size S. I'm going to explain in a moment what is a multi-partition rectangle cover. And this lemma basically uses that the polynomial that we're dealing with is multilinear, and there is this bijection between the support and the ones of the function. Those are the basically the main ingredients for those two lemmas. And for the other lemma, it's basically just a calculation, just a bunch of polynomial identities that you use. Okay, so now all we need to do, and what we did was to just prove a lower bound that is sufficiently strong for this F. And so that's it. Now I'm gonna focus on this part of the paper. So any questions before I move on? Good. So let's prove it. But first we need to define what we're gonna do, what kind of lower bounds we want to prove, and the basic. Okay, we're gonna fix a partition of all the partitions that I'm gonna talk now are bipartitions of the input variables for the Boolean function. Now we're only going to look at Boolean functions. We don't have no more polynomials, important. And all we're going to do is to, all the partitions that we're going to consider are bipartitions of the variables, and they are balanced if they are far away from the extreme 0 and 1 and n. And now, as I said before, we're going to prove a lower bound for the size of multi-partition rectangle covers. So I need to define it as a rectangle, and the rectangle is just a rectangle. Like you have but you need to define a rectangle with respect to a partition. So we fix a partition A and B, and then we interpret the Boolean hypercube over there as a Cartesian product of the hypercube defined with respect to A and the hypercube defined with respect to B. And the columns will be points in this hypercube and the rows will be points in the other hypercube. And we say that the subset of the hypercube R is an AD rectangle if R can be expressed like this rectangle over here. You pick a subset of the columns, and then you pick a subset of the rows, and every point in R can be expressed as a concatenation of a string in A and a string in B. So this is a rectangle. But for the things that we're going to do later, you'll only care about rectangles that are monochromatic with respect to the Boolean function that you're studying. So this kind of rectangle won't be that interesting. We're going to be interested in rectangles that are monochromatic, like one monochromatic or one rectangle. And and then just to make sure that rectangles are not just this kind of rectangles, but also more general structures. But it's just the definition is just like the definition is exactly what I explained before, just that it can be more general than the picture was before. Okay. So now we all know what is a rectangle, so we can define what is a multi-partition rectangle cover. And a multi-partition rectangle cover for a Boolean function is just a collection of points, collection of subsets of the hypercube, where the union of the subsets is equal to the ones of the function, and each point, each element of the collection is an each element Ri is an AIBI rectangle with respect to a balanced partition AIBI. And why is this definition interesting? One reason for that is that it generalized the usual two-party non-deterministic communication complexity of a Boolean function, which is in the case that we fix beforehand a partition, and then we require that all the rectangles in the cover are of the same partition. If you know what is the two-party non-deterministic communication complexity, it's kind of clear that they're the same object. Okay, they're not exactly the same, because here I care about the size And in that setting, people care mostly. Oh, maybe they also just care. Okay, they're basically the same, I guess. And maybe they care about the log of the size. Anyways, but today we want to prove lower bounds for the number of rectangles that you need to cover F. This number over F. And this that definition also generalizes the best partition non-deterministic communication complexity of a Boolean function, because in that setting we are allowed to minimize over all the partitions, and then we choose the best rectangle that are where all the best cover where all the rectangles are using the same partition. But the interest, like the difference between the previous thing is just that here we are allowed to choose the best partition. And using the same trick as Magnus explained before, we're going to use basically the same trick. We're going to use the expansion of G to be able to convert a multi-partition rectangle cover for F into a two-party non-deterministic rectangle cover for a certain disjoint function that I'm going to define later. But again, this is now our idea is to find a way of use the structure of the function that, as I defined before, this function F is very related to an expanded graph. And then we're going to use the structure of the function to reduce the problem of proving a lower bound for the multi-partition rectangle cover to the problem of proving a lower bound for two-party non-deterministic communication complexity, which is a well-studied object since many, many years ago. So this is so now I'm gonna focus on this part, but if you have any questions about the setup, you can ask now. There are two questions you can ask.
Is the cover disjoint or can they overlap?
They can overlap. I think if it is disjoint, I don't think there is a name for that. It is not from the document. For the if they're disjoint, okay, I'm not going to say that. They're not disjoint. There is a question over there.
These rectangles are not contiguous, right?
No, they are. They can be structure of this form, if that's.
And also, I mean, if you're saying that there is multi-party. You're saying here this multi-part rectangle cover. It is still a two-part rectangle cover, right?
Say again?
So you're saying that here,
where
we use the expansion of G to convert a multi-part rectangle cover. It is still a two-part rectangle cover you're using, right? Or there are, I mean,
I'm
yes,
going.
the product set is more than two.
No, in this I'm saying that I'm gonna reduce any multi-part, any cover of this kind into a cover of this kind. That's my claim. Was that your question?
Yeah, I guess the confusion is between multi-party rectangle cover and multi-partition. He means multi-partition there. So, yeah. No, so I think the confusion was about, so multi-partition just means that each rectangle can have a different partition.
Exactly.
Whereas it was confused to remain with understanding as multi-party rectangle.
Oh, I see.
Yeah.
They're different
Then you
things.
have more than two parts.
They're different things. Yeah, good. Thank you. Good. So let's prove this. And the idea, okay, we have a Boolean function defined using the expanded graph, as I said before. It's 1 if and only if the number of edges in the graph induced by S is different from 1. And then we want to prove that any rectangle cover of this kind has to use many rectangles. And in order, for the sake of simplicity, I'm going to just prove a lower bound for the best partition case, where we can choose the best partition, we can choose an entire partition, then we want to prove that the number of rectangles with respect to that partition is large. And, okay, so let's prove it. So the idea is that we have a graph G, and then we have a partition A and B, and what we are going to do is the same what Magnus did before, like in his presentation right before this one. We're going to find the big induced match in this graph, and now we're going to ignore the rest of the graph and just look at this induced matching. And okay, so this is the induced matching over. A matching is just a map from one set to another set. It's a bijection between one set and other set, and I'm gonna denote by C the set in A. Yeah, the set of points from A that are mapped to a set of points in B, and I'm gonna denote by D the set of points in B that are mapped from points in A. And the nice properties of this matching is that it is a reduced match, and it is very large in the sense that the number of edges is of order of n, where n is the number of vertices. And then what we do is just, we first restrict f to, this G is just a restriction of f to the set C and D that we have over there. And then we can, as G is just a restriction, we can now obtain a rectangle cover for G from a rectangle cover for F by just restricting the points in the previous rectangle. And then now we already reduced the problem of proving a lower bound for F to just prove a lower bound for the two-party non-deterministic communication complexity of G, where the partition is this C and D. Okay, so that's what we are going to do now. And the nice thing about this G is that it has this nice characterization of the ones, the set of ones in this for G. And it's just the set R G of R and S is 1 if and only if the cardinality of the intersection of S with the points mapped by the image of R with respect to this mapping, if and only if this cardinality is different from 1, as we can. It follows from the fact that we only consider this induced matching, and yeah, that's basically why we need an induced matching just to have this property. And the nice thing about this property is that it is basically a disjointness function defined as follows. And the nice thing about this disjointness function is that Razborov did the hard job of proving the non-commutative, non-deterministic communication complexity lower bound for this function back in the 90s. So now we are done. We just proved a lower bound for the best partition communication complexity of the function f. But that's not exactly what we want, because we want the multipartition. But for the multipartition, what we need to do is just to look deeper into this proof of Razborov and use the key lemma there, and then also combine with some different ways of sampling this matching that we can actually use that lemma in a very technical way that I'm not going to explain. Okay, so now this is the whole proof of our algebraic result that I stated before. So if you have any questions, you can ask now, otherwise we're going to move on. Good? So now I'm going to talk about some completely different stuff. I'm going to skip this thing because I'm running out of time. But you can interpret our results as saying that we cannot do hardness escalation for monotone classes because we know that, because the first result says that any simulation of low depth search by a monotone search will require very large ball load. This is a general thing of the results in this paper, but for the algebraic setting, the results are even stronger because it says that no information from the general circuit that we started with can be used to obtain, to substantially speed up monotone computations. And for me, this is a pretty nice statement, and that's the general idea of the results of this paper. But the interesting thing is that we don't have such a statement for the Boolean setting, and so yeah, that's a nice question. Try to prove a similar statement for the Boolean setting. But this is a workshop on algebraic complexity, so that's why I explained just the algebraic part of our results. But we also have a different kind of separation where we consider this class the radical of a class. Okay. We also have a different kind of monotone separation, but in order to state that result, I need to define what is a radical of a class, and it's basically what we would expect. The radical of a complexity class is just the set of polynomials such that there exists any integer, any natural number, such that p to that natural number is in C. which means that if we write down, if we raise p to the certain power, then we can compute p to that power easily. And the result that I just want to say is that we can show using the monotone, by proving monotone Boolean circuits lower bounds, we can show that Vp is not contained in the radical of monotone circuits of size n through some constant log n. And yeah, that was the result that I want to say in these further results. And the idea is just use monotone Boolean complexity using this reduction that was mentioned in Rubich and Yehudayoff. And yeah, and we also using the techniques that we developed to prove that lower bound in the algebraic setting, like that radical separation, we can also use to prove stronger separations in the Boolean setting, and also separate the power of pure dynamic programming approximation algorithms and really algorithms for a certain function. So that's it what I want to say for today, and we have some nice open questions. And thank you.
Yeah, any questions? Okay.
Is it reasonable to expect a separation that looks like d to the n when you're dealing with d polynomials?
D to the n.
I mean, the trivial. That's trivial.
Mm-hmm. But then for that case, you need d to be much larger than n to make sense, right?
Probably n is
So I was thinking of d and n as being comparable.
If d and n are
I'm
comparable.
not dealing with the multilinear setting or anything.
I think it makes sense. Like for our setting, I think k can be up to our set for our in the lower bound that we showed for the constant degree polynomials, the degree can grow as a function of n, but it cannot be too close to n. So if d is larger than n, then I guess our results are not valid in that setting.
No, but then you can go to, let's say, the degree being, let's say, n by 2, and then you get n by n. Yes, yes. But the lower bound I thought looks like n to the big omega of k.
Yeah, but in the case that k is a constant.
Oh,
It could be a growing function with n, but then the lower bound will become worse.
So the lower bound is essentially the sparsity.
Yeah, for constant degree polynomials.
Yeah,